So, welcome everybody. Excited to have you all here today. Thank you so much for joining us. My name is Sophia Kim. For those of you who don't know me, I'm the director of the Science Learning Institute at Foothill College, and we host this series. I guess I was going to say quarterly, and it's kind of been variable depending on the time of year. But it's called the STEM Equity Seminars for Owls, and we invite academics and researchers from all over the country to share about their academic path as well as their career research. So we're really excited today to host Dr. Enrique Gómez, and I actually got introduced to him by our very own Jeff Matthews, who's one of our astronomy instructors, for those of you who don't know him. So he's actually going to introduce Dr. Gómez. And how we'll do today is we'll have Dr. Gómez do his talk. He has some slides to share, and then we have time for questions in the chat, or if you want to come off mute. And feel free to put questions as they come up in the chat, but we'll kind of find periodic times where it makes sense for Dr. Gómez to answer those questions. So thanks so much for joining us again. And I'm going to turn myself off the spotlight, and Jeff, and if you could take it over with an introduction.
Great. And so thanks, Sophia. And I want to express my gratitude to Dr. Enrique Gómez for coming in and speaking with us today. Dr. Gómez is Associate Professor of Physics and Astronomy at Western Carolina University. And we met, what was it, last May, somewhere around there. We met in an online email discussion about, what was it? I think it was about like going back and forth between our 2D view of the sky and the 3D distribution of objects. And so we were having this really great conversation online about this topic and how to help our students. And then I get this little line, in parentheses, and I received this in an email saying, "Hey, by the way, Jeff, I went to De Anza." So this is Dr. Gómez telling me that he went to De Anza back in the 90s. And so I immediately knew, I was like, hey, we need to ask him to come in and speak in in the seminar series because, I've been, Sophia's been doing these talks for a few years now, and we always love to have people come in and talk about their pathways, but we especially love to hear from people who have been through our schools, right? People who are from here, or have had experiences here. And so it'll be great for our, so I knew it'd be great to have you in and speak with us to, you know, talk with our students about both the cool research that you're doing and your pathway getting there. So a little bit more about Dr. Gómez. As I said, he went to De Anza back in the early 90s, went to UC Santa Cruz to get his Bachelor of Science in Physics, and then the University of Alabama to get his PhD in physics back in 2006. And so then he studies supernovas and gamma ray bursts, which are topics which the students who I see on the list here are all going to be saying, "Hey, we just learned that last week," and and so this will be sort of a really nice additional depth for them. And but then also more recent work doing studies of cosmic ray radiation in the upper atmosphere, and if I'm correct, that's been work with students, right, using balloons. So really looking forward to hearing about that. But when I asked Dr. Gómez what I should emphasize in his introduction, he really said, really wants everybody to understand that he seeks out opportunities to do science as public engagement, as community building. And to that end, I want to highlight something I noticed in the acknowledgments of your PhD dissertation, where your opening line, Dr. Gómez's opening line was, "Research is always a community-supported endeavor. None can claim that the study of the world can be accomplished without the constant interaction and dialogue with other human beings that share the same desire for understanding and meaning." And
I
that
wrote
statement, you wrote that. Yeah. I, I wanted to go take a look at some of your research work and, oh, hey, dissertation. And that is so true. And I'm so glad to see you here today. We got a couple dozen or, more than a dozen students in here who are people who share that same desire for understanding and meaning. And I'm really glad that you can be here with us today, Dr. Gómez. to share discovery and your path to discovery.
You are so kind. Thank you so much, Eof, and thank you so much, Sophia, for the kind invitation. I just need to do a quick sound check to make sure that you can still hear me and all that. In a moment, I'm going to start saying some slides, but
If you could turn up your volume a tiny bit more, Dr.
so
Gomez,
I
that would be
am
helpful.
checking how are we doing. Does that help?
A little bit more.
How's that?
That's good. Yes.
That's good. Okay. All
Yes.
right. Thanks for that sound check. And don't be afraid. And sometimes I forget that I'm a teacher and I forget to use my teacher voice. All right. So yeah, I just want to say, because I've been academic now for a good 17 years, and one of the things I do is I do a lot of work with, for instance, transfer from community college into the UNC system, the University of North Carolina system. And looking back at my background and looking back at the work that I've done through as being academic and how I went through college and all of that, and I'm still blown away by the quality of education that I received at community college. It's one of those things that it just cannot be sort of ignored, because I keep looking, for instance, at the mathematical backgrounds and the preparation that some of the students are coming in, and I'm saying it's like, really, I really wish that we kind of saw more schools do as good a job as the Anza College and no doubt Foothill College are doing in preparation for this. And I still think quite fondly to some outstanding math and physics professors I've had that's long since retired, obviously, that really laid that foundation. One quick thing that I want to do is that I really want to highly encourage you all, as you are considering this path towards transfer into a four-year university, whatever your career might be, to consider looking and getting that associate's degree, that A degree, as one of those things that kind of is a fallback and also kind of like provides that guaranteed of transferability really across the country. So it's if you can kind of like take it upon yourself to investigate it. That's not something that I did. Not that I was needlessly harmed by this, but we know that students tend to have an easier time if they go and take the time to do this. So one thing I want to build up also is this concept of community engagement. I'm going to share my screen with the hope that you'll be able to see it. And Sophia, if you could let me know if things are not visible to you all. Okay, so let me just go ahead and do this. And
Yep. We
and
can
I'm
see.
going to go into full screen presentation mode. Am I still good?
Yep. So far we can
Okay.
see. Yep.
So we have that. So here we have like images of the work I've done with students. And this is actually an image that some of my students, along with Virginia Tech students, did of essentially the shadow of the moon over Missouri as well. But this is actually kind of began. And when I was a high school student, I went to Los Gatos High School, a little bit far
Dr.
south.
Gomez, can you get into presentation mode? Because that'll help us with seeing it a little bigger.
Okay, so I wonder if I can go into presentation modes and
Down in the lower right-hand corner, one of those little options is like a bigger screen, way down tiny in the bottom right-hand corner.
right-hand corner. So I'm going to see, is this presentation modes? I think
It's
I
the
did the
one,
wrong one.
or if you go up to view, actually up top,
Oh gosh.
and view is one of the options. And then I
Let
think
me
if you
do
click
that.
on view,
Screen, show presenter view. Am I right?
well, go over to, oh, are you sharing the, do you have two screens right now? Because you might be
On
showing,
one screen.
okay. So go up to the view menu item over, so see how it says home, insert design. I'll go over to view. It's like the second to the last one on the right next to help.
I'm sort of like having a hard time here.
Oh, let me see.
Oh, wait, hold on. Maybe I need to end my presentation, start from the beginning.
Okay, let's give that a try and see.
Sure. Okay. Let me come over here and see. I'm going to store down and maybe kind of like go into, I'm going to end my slideshow and then I'm going to start from the beginning and see if that helps. So I'm going to come from here and then the options I'm looking for look like, see if I can actually do this camera screen, show presenter view. I don't know whether that helps or not for this part.
Maybe unshare your screen and then try sharing it again because it seems like you're seeing something that's different than what we're seeing.
Yeah, it looks like it's different. So let me
Yep.
just go
So go
back.
ahead and unshare.
Okay, so I'm going to, I know what the issue is. Hold on a second.
Okay.
So
Okay.
I'm going to do a share. I'm just going to share my entire screen. How about that? I don't know
Okay.
what
Okay.
the issue is. So let me go ahead and do that and share. And I'm going to start from the beginning and see if that helps. So, okay, is that better?
Much better. Yes, we're
Okay,
good.
there we go. What I'm
Okay.
showing here, I show like a picture of a Texas Star Party. And really, I started as an amateur. And I was very deeply engaged with the San Jose Astronomical Association way back in the 1990s. I hope they are still active. I'm still hope that some of these guys are still okay. But the thing about this is that this gave me like a great education, even going back as high school, in terms of just connecting with people who are passionate about the sky and wanting to share the sky as well. So I took that ethos of essentially sharing the community. And whenever I come in and I want to kind of like build my life in a community, that science is something that is best shared if it's not done alone, but coming together. And whenever possible, if we can engage people, not just students going to college or graduate students, but also members of the community as well, that's one of the things I want to bring with. So, for instance, I was very active as an amateur astronomer, and actually, this is not a picture of me, but it looked very more similar to what these kids are doing. And that is that I had a pair of binoculars, and essentially what I did is that I participated with the American Association of Variable Star Observers, the AVSO, to submit observations of the changes of brightness of stars over time. And I was shocked a couple of years ago as I was going through the databases and my user, and I found out that observations I submitted back when I was 16 years old, they're part of the database. I could still access them. They're still good. So it is like, okay, well, it's cool. But could I bring that experience back to, say, kids or with college students or just members of the community? That's what I've been hoping for. So, in my life as an academic and also as a member of the community, I've reckoned that I probably have shown the objects through my personal telescope or university telescopes to roughly about 9,000 folks, right? So, this is something that I do in my constant engagement. Professionally, this is what it looks like when I work with computerized telescopes or robotic telescopes. I'm showing you one of the telescopes that I've used over at the Las Cumbres Observatory, which is based in Santa Barbara, California, but they have professional telescopes really spread all over the world, right? Whether at Haleakala, Hawaii, or the Canary Islands out there in the Atlantic Ocean, or South America. So this is the type of telescopes that I've had myself and my students have used. This particular telescope is supposed to be deployed in Tibet. That would be part of China. And this is sort of like the type of stuff that I do. I have like students, for instance, kind of like take images of supernova explosions in galaxies whenever that happen. And I'm just going to highlight it in my cursor. Like right here, a couple of years ago, there was an explosion in a galaxy, relatively nearby galaxy, M81, M51. And I also kind of teach my students how to create color images of things. So I took this image along with my students of the Eagle Nebula, the Eagles of Creation, which you can find as Hubble Space Telescope images. They are right there. And also how to kind of like assemble this based upon using filters. So I teach also about astrophotography too. And actually, let me just say, I cannot believe that I get paid for the stuff that I do. I really don't. Right. Is that I get to go out there, look at the sky, have fun projects, work with kids in K through 12 schools, be part of the community, reach out to amateurs, and essentially do some amazing things and travel to conferences and also to do experiments elsewhere. I also use radio telescopes. We have some radio telescopes that we're refurbishing in here in North Carolina, but I also use the Greenback radio telescopes in West Virginia. And I did not take this image of the famous black hole at the center of the Milky Way galaxy, Sagittarius A star. This was part of the collaboration called the Event Horizon Telescope. But I have my students aim radio telescopes right at this and take spectra of the gas clouds around this black hole and measure things like their velocity around the black hole. That's something that I do, right? And I cannot believe that I have undergraduate students who are not even physics or astronomy majors. They are education majors. They are business majors. I have them do this. What am I thinking? So this is the type of objects that I'm interested in. I've had students, for instance, monitor exoplanets. Whenever you have a transit, that means that a planet comes in between a star and us. We cannot resolve the planet, but we can monitor the dip in brightness in the star as the planet goes in. And this is actually very important because the James Webb Telescope is in the middle of a campaign to monitor these exoplanets, to image as well as get spectra of the atmosphere of these planets to determine whether you have the chemistry of these planets will be ones that you will find from, say, whether they be livable or not. Most of the time they're not, but I had like a student monitor exoplanet around a star called Qatar 1, and this is what it looks like. This is actual real student data showing the dip of this brightness. Another thing that I do is that I monitor a type of star called cataclysmic variable stars, where you have two stars very close together. One is a white dwarf. Occasionally, one of the white dwarf will have an accretion disk of material that slams into the white dwarf, and sometimes you get ignition. Sometimes you have thermonuclear reactions, and for a very brief period, this star can outshine the sun by 100,000 times, right? And they're seen clear across the galaxy. And I have, for instance, like students kind of like monitor the changes in brightness, and try to do, say, a periodogram, go and do a fast Fourier transform to do this. Where did I learn about fast Fourier transforms? I learned it in community college. I learned it in a class called ordinary differential equations. That's where I encountered this. Now I have the students use those exact same mathematical tools to monitor the changes of brightness on the disk around colliding stars. And this is what it looks like when one of my students do this. And one of the things that's wonderful about this is that this student I have here, she's a non-traditional student. She's a mom. She's a single mom. She wanted to have a research project in astronomy that she could do in her own time, knowing that she has to worry about childcare and complete her classes. Well, if you have a campaign using robotic telescopes where you don't have to travel and you don't have to spend all hours of the night, then she can complete it within the semester. And the graph that I just showed you was work that she did herself. Not only that, but I have like some cataclysmic variables like SS Cygni. Here's a picture of this that I took, and this is what it looks like. And as a part of an intro astronomy class, well, we adopt this as kind of like a class pet, and the students can get extra credits for monitoring this star over a period of the semester to see any bright changes. And as a matter of fact, last year, this student, who's an education major, Liz Scruggs, monitored the star when it was going through an eruption, and she was the first person on planet Earth to catch the beginning of that eruption, and she submitted that to the AAVSO, and she got class credits from this, and she got a NASA sticker from me because, hey, I'm not above bribery. But anyway, yeah, this is one of the things that I do. Here you have like a student image of a galaxy with a supernova. Where's the supernova? Sometimes you have to hunt for it. There it is. This is an archival image. This is the exact same galaxy with a supernova. And this was essentially taken with a Perth Observatory in Australia, even though we're North Carolina. Here's another example of a supernova explosion with taking a Fan Mountain Observatory in Virginia, and this is student work showing the same effect. I'm worried about stars that blow up. And for instance, what are the chances of one of the stars actually erupting here? Here's a picture I took of a star called Eta Carinae, which is deemed the one of the most dangerous stars in our own galaxy. It has a mass close to 100 times the mass of the sun, extremely luminous. One of these days, soon, it will go into a supernova. We don't know what it would look like. We are at a safe distance from these things, but can we survive? If we happen to have one of these things erupt and it's less than 1,000 light years away. Good question. So here's an example of a supernova in our neighborhood. This is a supernova remnant, actually, taking a combination of X-ray images as well as visual images. This is the supernova remnant of Cassiopeia A, observed by Juan Tycho Brahe back in the 1500s. So one of the things I'm interested in here too is that the sun seems to be going through a region in space called the local bubble. The local bubble is the debris field of several supernovae that went around at the same time. So this supernova erupted, and we kind of entered this region with increased charged particles. And turns out that this happened around the time when humans appeared on Earth, right? Is there a coincidence? I don't know. But we certainly are living right now in a radiation environment in a part of a galaxy which is not typical to conditions here on Earth. So we are seeing far many more charged particles coming closer towards the center of the Earth than you normally would. Okay, so this animation kind of like shows what the sun was doing as this expanding bubble from supernova debris kind of expanded, and now we are in the middle of this. So we entered roughly around 6 million years ago, and we see the signature of this also in isotopes. For instance, iron 60 is an isotope that should decay very quickly. None should have survived from the beginning of the solar system. The only way we can get this is not a decay product of radioactive material of other isotopes, but enrichment from supernova explosions. Other things I've done, I'm interested in what it looks like for stars when they enter the local bubble. Here you have a star taken in the UV by a mission that's no longer operative called the Galaxy mission. And what's interesting here is that this star is a star you can see with your naked eye. It's Mira. It's a variable star. Variable star astronomers have known this for the 1700s at the very least. What's interesting here is that this star right here, as it enters the local bubble, this thing sends a big cloud of material, a stellar wind that gets impacted by this soup of charged particles and produce a bow shock. And yes, it looks like a comet, but this comet tail, quote unquote, it has a length of several dozens of light years across. And one of the things I do is do simulations of this, of what it looks like when a star like this kind of enters this debris field. So in the right-hand side of this image, you see kind of the shock wave of the supernova explosion debris field of the local bubble. And this is what the star's clouds do, the material as it plows through with various types of density models that you can have. And this is actually what it looks like when I do simulations to try to kind of reconstruct what the debris field look like as well as the bow shock. And sometimes the simulations look really wrong, and that's how you know that one particular density profile, both of the shock wave as well as the star, is not matching what you see with simulation with the actual observations. But how does this show up here on Earth? So charged particles from supernova explosions and maybe other astrophysical process provide something called gamma ray bursts. Cosmic rays. Although gamma ray bursts are a source of cosmic rays, particularly photons. But anyway, a typical cosmic ray would be a proton, although you can find other things. And what happens around 100 kilometers above the surface of the Earth is that they impact matter on the atmosphere, producing a shower of secondary particles, exotic particles that people typically don't see, like antimatter, like electrons, positrons, protons, antiprotons, weird particles, pions that decay very quickly, as well as muons. And muons are the ones that typically come and survive to the surface of the Earth. But as you go higher and higher in the atmosphere, you start to pick up more of that radiation, and the level of radiation kind of increases. So we're interested in trying to characterize what the energy of these particles are. You know, this is a spectrum showing the energy of a typical cosmic ray primary particle as well as the flux, how many events we have, and you can see that it gets more and more rare the more energetic the particle goes. But it's a big mystery ultimately what these features are and what actually produces some of these particles. Other thing that's kind of interesting is that there seems to be an association between cosmic rays and lightning, in a sense that cosmic rays ionize the radiation of the atmosphere, producing pathways by which lightning could actually be more common, particularly cloud to ground lightning. And another thought would be that maybe that has affected evolution. Maybe. Could it be that the reason why hominins left the tropical jungles of Central Africa into the savanna is because there were more forest fires triggered by more cloud to light lightning made possible by more supernova explosions? We don't know. So that's part of the reason why this story might actually connect with evolution here on Earth, particularly human evolution. But practically speaking, how does this actually show up? So the sun itself produces something called a solar wind, which is essentially charged particles that travel at hundreds up to 500 kilometers per second. And as these charged particles from the solar wind meet the interstellar medium that has been enriched by supernova explosion, you have a region called the heliosphere. So we are inside the heliosphere, deep inside. We have evidence from the Voyager mission, Voyager 1 and Voyager 2, that they have entered the region of impact between the interstellar medium and the heliosphere, and you have a strong signature for this. But here's another thing that happens. The sun is a variable star in the sense that it goes through 11 solar cycles. So right now, we are in the midst of a peak, one of the strongest peaks of solar activity, which means that the radiation produced by the sun and the heliosphere becomes bigger as more charged particles are emitted, which means that cosmic ray particles coming from the outside of the solar system have a harder time penetrating deep inside. So what I'm showing you here is the sunspot numbers for the past cycle or so, showing that we were at the minimum roughly in 2020, and looks in 2024, 2025, we'll be reaching the sunspot maximum. So we're becoming more active. The point there is that I've been monitoring cosmic rays really for the past decade, looking at the signature of the penetration of cosmic rays at various stages for this. For back in 2020 and earlier, we had a more cosmic rays penetrating because the solar wind was weaker and the heliosphere was smaller. Okay, so this is what it looks like for me when I was younger and had more hair. We've been sending balloons to the Earth's stratosphere. This is the rooftop of the building where I teach. And here is a reconstruction using Google Earth of a path of one of the balloons launches from this past year. Okay, showing that we went good way above the city of Charlotte, North Carolina. And this is what our balloon payloads look like that are there to take pictures and also to try to collect radiation data as well as pressure density, whatnot. So this is what it looks like when you have a GoPro and we launch. And yes, I actually live in this area right there. This is the middle of campus as we launch it. And then this we go through the clouds. And this is what it looks like over Lake Lure when you are hitting altitude of about 70,000 feet above sea level. And indeed, yes, the Earth is curved. That's gratifying to see. So, and we have to go out there and retrieve it, right? Which means that we have to go out there in a country. And I'm so jealous of those of you there in California because you don't have that many forests, meaning that when you have balloons that you launch and you have to retrieve, you just walk in the middle of a national monument or something or in a field and you pick it up. Here, what we have to do is kind of like dig it out from the top of from the top of trees, usually, right? And there was one incident in which we launched a balloon. It didn't do the way it's supposed to. I underinflated, went clear across Virginia and landed in the ocean, what this was not supposed to do. And it was lost in the ocean for 2 weeks before this high school teacher found it on out the outer banks of North Carolina. Here you have a police officer that indeed confirmed that this was not suspicious. It was not a bomb, found our contact information, and I got our science and pictures back, including a picture of our payload in the middle of the Atlantic Ocean. So anyway, this is what it looks like when you have like a student experiment that you kind of put inside of a payload and you launch in there. You have to get, alert the FAA and FCC that in fact you are doing this. And this is typically what we observe. So what I'm showing you here is the altitude in centimeters above the surface of the Earth. And this is the counts per minute. And indeed, you see that as you go higher into the atmosphere, you hit the maximum number of particles, and then you get lower indeed. So I do simulations also to try to reconstruct what those charged particles do. Okay, and well, this is more pictures of essentially our launches. We use either helium or hydrogen to launch these things, and we track it. We actually recruit amateur radio operators, ham radio operators that can pick up on the digital packets of the telemetry of this and track these things for us. And we also have multiple ways of tracking this once this thing goes down, including a beacon that amateur ham radio operators can pick up and follow and find for us. Okay. We also launch in the middle of eclipses. We've had several eclipses. So for instance, this is what it looks like in the right, in the same altitude, in the sky, same time of day when we had a regular day. And then on the right, whenever we had like an eclipse happening, in this case, October 14, 2023. More pictures of what it looks like to launch and having to retrieve this. And also this thing, so it looks like this is a drone image from a local sheriff drone operating and seeing where our payload ends up, and usually at the top of trees. We usually have to go out there and hide. And of course, if we are in North Carolina, we are blessed. We having lots of students that also are hunters that can also have good wilderness skills to help us kind of go there and sometimes knock down with essentially hunting arrows. And sometimes we have to hire professional climbers to come in and retrieve for this. And yes, we are the Catamounts. That's a school mascot. So each one of those guys is named after a catamount. And we recruit elementary school kids to draw the mission logos for each one of our payloads, just like NASA does. As a matter of fact, here's my kids, and the type of electronics that we have are things that you can buy online for just a few dollars. So for instance, this is an Arduino. If you're into robotics or if you do into amateur electronics, you know about microcontrollers. So that's how we run our operations. And this is what it looks like when we kind of assemble some of these payloads, put them together. Here you have a radiation shield with a Geiger counter that measures the radiation for us, a logger shield, mount that with a logger pro, and then you just send off into space or near to the edge of space. So, and one of the things that we found, for instance, is that depending upon different times, so for instance, here I'm showing you different radiation counts at different dates or different altitudes. And what you see, in fact, that it was true that when you have a radiation minimum back in 2014, you had more radiation. And as you go progressively now, the number of radiation in the atmosphere has actually dropped. And the units here is going to be microsieverts per hour. We kind of check back with other radiation monitors. So for instance, in Finland, there's a radiation monitor that measures neutrons. This is a way to see what cosmic rays are actually doing. And indeed, in 2024 into this year, you can see that's actually been dropping, meaning that the sun has become more active. And there's a team out there in California, Latitude 37, that has been launching these operations. And they also, their balloons are showing exactly the same thing, that the level of radiation has precipitously dropped as the sun has become more and more active. Something else that we've done for fun too is that we have done this with solar eclipses. In 2017, we had a total solar eclipse over here in North Carolina. This past April 8th, there was a total solar eclipse through the center of the country going through Fair, Missouri, and we partnered with Virginia Tech to kind of like do a balloon launch at that time, and we had radiation monitors. And this is, we went to a small town in Terre in the border with Arkansas to do this. This is what it looks like when you have a team of students launch balloons. We had to inflate this, and you have to launch this at least an hour or two before the actual event to make sure that this thing is up in the air. And this is a picture of what it looks like taken from this student GoPro showing the shadow of the moon. And to just give you some context of scale, this was taken around almost 80,000 feet above sea level. The shadow that you're seeing there spans about 150 miles across. So this is the umbra of the moon projected on the surface of the Earth. And what you're seeing here are 4 states. Uh, uh, I believe that you are seeing here not just Missouri, but also Illinois, Kentucky, and bits of Arkansas. And this is what our students took that on the exact same trip. And I think I have a movie that goes along with this. So we had a payload with a GoPro that showed you actually what it looked like and what the shadow of the moon looks like on the surface of the Earth, which is actually pretty cool. So this is all student payload, student working together experiments that the students themselves design and tested. And it's actually excellent. And actually, one of our payloads wasn't actually really high when the eclipse happened. It started to begin to go. And this picture, what I'm showing you here, looks very chaotic, but you can see the sun that was in the middle of the eclipse, and you can see the planet Venus a little bit below. But this is absolutely one of the best pictures I've ever taken, that student has ever taken. I'm completely blown away because this thing went out and actually landed in an area on a wetland. And what you're seeing down here in the bottom right is an image, a reflection of the total eclipse on the ponds, looking down on the ground when this happened. So it's like, oh, okay, who's ever going to take a picture of an eclipse like that? So when we went and we tracked this, we launched it from Tear, and for whatever reason, this decided to actually land on the Mingo National Wildlife Refuge, and we had to get one of our payloads. We actually launched several payloads. One of them we could retrieve, and the next day we had to get a game warden on a canoe to please get that balloon payload from us. But one of the things that we're interested there is to take this to a next level. As we're speaking right now, just like about an hour or so, I had like a student group who is an engineering capstone team that is working hard to build a version of the payloads that we launch into space. But we want to propose a CubeSat mission to NASA. CubeSat is a satellite which is about 10 centimeters by 10 centimeters to 10 centimeters, essentially the size of a box of tissue. These things are either launched from Virginia on rockets, or they are sent to the International Space Station to launch and to track. These things typically last up to a couple of weeks, but we like to be able to do experiments with very much the same experiment design that we have. So this is what it looks like. We have a capstone engineering team that 3D prints various prototypes and also designs the boards that will be the brains of this mission. And this is kind of the type of work that I do. So at this point right here, looking at the time, I'm going to stop my share, and I'm going to allow you all to ask questions. Thank you so much for your kind attention.
Thank you so much, Dr. Gomez. That was super interesting to just see all the pictures and the photos of everything. Yeah, so would love to see if students have any questions. Jeff, if you have any questions that you want to kick off with too, go ahead.
Well, sure. Okay, do you have 5 hours? Okay, lots of questions. So, I, uh, so you said that you have students doing projects, where they're doing these observing projects. Are you having them doing that using the LCOGT telescopes? Or,
Yes.
yeah, okay.
So I do LCO, and I also have account with a network of robotic telescope called Skynet. And yes, it sounds awful lot like Terminator, ha ha ha, right? I guess it's not avoided, but this is the flagship telescopes are in Cerro Tololo, Chile, as well as Saskatoon, Canada, and also in near Perth, Australia. But we also have like several telescopes spread all over the world, not just North America, but also Poland and yeah. So that's what we have. And one of the challenges I have, and I'm sure I appreciate it, is that when you're trying to get students to get in the mode of thinking about science projects, it's really hard to come up with a project that's tractable, that's able to do within one semester. So what I've been doing is hunting for the process of finding ways of things that students can assemble, can actually do, and can get results, can write up, and even submit to conference as well. And one of the things that's, for instance, remarkable about with the balloon projects is that I've had students, for instance, start really from scratch and even submit proposals to the Honors College to get funded for a few $100s, and then put together a mission, design it, launch it, retrieve it, analyze the data, put together either a poster or a report, and then submit it to an undergraduate research conference. And that happens within one semester. And they get credit for that. And I'm absolutely blown away by this, that it's actually possible to do. All other things I've done, for instance, with the robotic telescopes, is that for instance, monitoring of exoplanets. You can, with robotic telescopes, they allow you to do the following. They allow you to get around to the fact that sometimes it's cloudy, sometimes the telescopes are down. You can send a request to a network, and whatever telescope is available to monitor a particular transit event, things would be allocated so you're able to do that, right? And those are actually a real contribution. The AVSO and other organizations are actively soliciting folks to monitor exoplanet transits, not because we want confirmation whether the exoplanets are there, but because sometimes what happens is that you have timings to it. Sometimes you generate a model to try to anticipate when the transit event is going to happen, and sometimes there's a drift. Sometimes the transit happens late or early. And what does that mean? Well, that means that the ephemeris means to be corrected, or there might be other things, like there might be other planets in the system that are actually altering the orbit. And the reason why that's important is that with the James Webb Telescope, you need to catch that moment in which the disk of the planet enters the disk of the star. So you catch that moment where you can get an absorption spectra of the atmosphere of the planet. So if you have a much precise, reliable ephemeris, all you have to do is just send a request within a few minutes. Otherwise, you have to have the detector open and running on the James Webb Telescope for an hour or so. So far, transit studies by really volunteers have saved already tens of thousands of hours of monitoring time on the James Webb Telescope. So that's the scientific value for this. Ooh, I'm looking lots and lots of
Yeah,
questions.
there's some questions. If you want to just field them in the chat as you feel like they make sense. It looks like Vanessa's question about the physics concepts, she kind of refined. So that's one question. And then the gamma rays is
So
another
the
kind of
thing about
question.
this is that it brings everything. So PV equals nRT is the equation that you want to do to figure out how much gas you need to put into the balloon, which is what I messed up, and that's why that balloon ended up in the Pacific. Don't do that, right? You make mistakes. Yes, that happens. Don't do that. And the FAA does not like it when you make mistakes like that, right? Because these things are supposed to pop and come down within an hour or so. Don't do that. Other physics concepts, well, essentially charged particles, right? Things having to do, for instance, with Wien's law is the way that we understand or make sense of the temperature of objects that are thermal, such as stars, or essentially gas clouds. Use spectra analysis to look at the spectra on the radio of stars, the 21 millimeter centimeter emission line of hydrogen, and the Doppler shift associated with it is how we figure out how fast gas clouds are moving around the center of our galaxy, or how fast they're moving relative to us. And hence, you can measure the mass of the entire Milky Way galaxy by looking at how different clouds at different distances from the center of the Milky Way galaxy rotate. So these are all questions like that. And Vanessa, I hope that I answer some of your questions. I see a question from Kevin. Do the gamma ray bursts still have energy and momentum? Well, and the answer is yes. And it kind of goes like this. So the thought is with a gamma ray burst, and I didn't really go into this, but the thought about this is that it's a very special type of supernova that produces a gamma ray burst, because it's one that allows jets of material coming from the newly nascent black hole to be ejected out and break through the atmosphere of the star, causing an emission from relativistic material traveling at a bare fraction of the speed of light. So that blast wave too has essentially have energy and momentum. And I remember, for instance, the question in my dissertation, the first question in my dissertation was essentially, can you essentially derive based upon conservation of energy, conservation of momentum, what essentially the distance that a blast wave will actually travel after the supernova would go, right? So you always have to use those, right? So Kevin, I hope that I answered your question. Vanessa asked again, is there any fundamental physics concept that the professor thinks is important for undergraduate students to focus on? Well, here's the thing. It's all good, and you don't really know. You don't really know what's going to be important. One of the things that physics does is that it serves almost as kind of like the liberal arts for the entire for the entire sciences. You need to know a little bit about everything, in addition to having a whole bunch of problem-solving techniques that are portable and applicable to a wide variety of areas, which means that if you've taken physics, even if your degree is not in physics, if you've taken enough physics courses, you can come into an employer and essentially show how you can solve a problem. And more than anything is the uh, uh, problem-solving style that physics brings, kind of starting with the general concepts and the fundamental principles, and work your way down to the application of those concepts to individual circumstances. That goes such a long way towards organizing your thinking about assembling a solution to a problem, fitting a model to data. So I think that it's all good. So I would say, I mean, really, it might seem that as a physics student just starting up in introductory algebra or calculus-based physics, that you're looking at things that are actually very boring, like pendula, like, for instance, cards going down an experiment or things like that. But you have to keep in mind that what we're trying to do is train you into a particular style of problem thinking, and that's what you have to focus on. And Vanessa, I hope that answered your question. Ooh, Sophia, you had a question. Okay,
But
coming
I'm just
down.
telling the students they can ask their question.
See, yeah, just look at that. Michael, you ask a question. So the heliosphere has a bow shock. Does that suggest it's moving on its own in addition to the expansion of the universe? Ooh, okay, all right. So a couple of things are actually happening with that question. So you and I are going around the axis of rotation of the Earth. That's one level of motion. In addition to this, we're revolving around the sun. That is one way in which we're moving. In addition to us, the Earth and the sun are also rotating around the center of the Milky Way galaxy. And I believe, in the latest that we know of, that it takes a good 200 million years for us to actually um, go around one complete orbit around the center of the Milky Way galaxy, which means that dinosaurs were on the other side of the galaxy whenever they died, right? They passed away, right? Actually, no, hold on a second. The first dinosaurs were about 200 million years ago, which means that we are roughly in the same neighborhood of the galaxy when, for instance, the not the the Stegosaurus, right? This Stegosaurus was around 200 million years ago, right? So yes, we are moving, right? But in addition to that, we are moving through a particular medium, which is going to be the interstellar medium. And even though it seems like it's odd, because we know that space is a vacuum, well, yes and no, in a sense that the density of atoms in between stars comes out roughly to about 1 atom per 100 cubic centimeters or so. So essentially, something about the size of my fist or so would have sort of like an atom. And that is enough so that it does make sense to talk about sound in a weird way, in the form of pressure waves. So what's going on with bow shock when you have, for instance, the sun, that it would be traveling faster than the speed of sound in a medium, it will produce a bow shock by the exact same reason that a boat on the surface of water that is traveling faster than the speed of sound in the water will produce a bow shock as well. Okay, so it's moving on its own. And then a question, Michael, that says, in addition to the expansion of the universe, and actually, well, let me just put it this way. What would be a reference frame that we have? And in astronomy, we have something that's called the cosmic microwave background. And the cosmic microwave background is radio emission coming in from right off the Big Bang. So you could use this and talk about the motion of the Earth around the sun, or the sun around the center of the Milky Way galaxy, or even the Milky Way moving around through its global cluster. You can talk about their motion, say, relative to the cosmic microwave background. So you could say that. Okay, and let's see. Going down here, and Michael, I hope that I answered your question. But coming over here, let's see. If gamma rays have no mass, how do they have energy? Hmm. Ooh, oh boy, how am I going to tackle this? Do I actually understand light well enough to talk about this? Well, if you can think about the following, to the extent that it means to say that light is a wave, and a wave has things like frequency and wavelength and can propagate, you can see that it has energy, right? But it doesn't have momentum because it doesn't have mass, right? So that would be something that you can have this, and yet they have pressure in the sense that you can leave, for instance, sort of like a piece of paper out there, and it would, if everything's still and you have everything controlled, it will begin to drift if you are shining light on one side, because there's such thing as radiation pressure. The amount of energy per second, or the intensity of the energy that gets expended per second, does translate that into an effective pressure. So yeah, gamma rays do have energy, but here's the thing though, and that is that you can also talk about light as if it were a particle called a photon. It actually does make sense to talk about this. So then the more interesting question would be, well, what is it? is light a wave or is it a photon? Is it a particle of light? And what is it that's actually kind of like vibrating out there that is producing this wave? Well, we say that's a electromagnetic wave, of course, but you have two different models of light to describe this. And if you create an experiment to measure the particle nature of light, you will measure the particle nature of light. If you measure the wave particle nature of light, you will measure properties of waves. So we have two different models that don't seem to relate. So we have this duality, and we have never resolved that in science. So to a certain extent, is that part of the reason why it's hard to answer this question is that ultimately we cannot really say what light is. We have multiple models that are contradictory that follow different things and give you different results. So it's very satisfying. But there we go. So again, it's an excellent question. That is a good physics question. I hope you study some more physics too.
Enrique, I have two questions.
Absolutely.
One is bigger and one is smaller. So you answer whichever one. Do you take outside students as part of summer research projects? I know, for example, there are REUs at various universities. I don't know if you have some similar mechanism where you can host students from, say, Foothill or De Anza to be summer interns. And then my second question was, if you could share a little bit, I guess, what your own academic path was. I know, we know you went to De Anza, you went to Santa Cruz. Were you always interested in physics and astronomy, and how did you kind of land where you were? So whichever one you want to take first.
Oh, okay. Huh. Which one do I want to take first? So maybe just quickly answer is that I've never had a research experience for undergraduates. It's one of the things that you have to ask funding for. So right now, my current grants don't have stipends to kind of like take students outside of it. Maybe I should. Maybe I should. Okay. So now I'll consider that a kick on the pants. So get my act together if there's enough interest for that. But I mean, if anybody's interested in either using robotic telescopes, doing astronomy, or doing high altitude balloon research, just shoot me an email, and I'll just connect you with people that I know do take REU experiences if you're interested, right? So it's not with me; it might be with somebody else. But going back to the my academic pathway, so it kind of goes like this. All right. So I did something that's slightly non-traditional because this is the trajectory for someone who is an astronomer, and that is that you typically get a physics undergraduate, right? And you go and apply to grad school to either a physics program or an astronomy program. There's enough overlap between physics and astronomy that it's possible, for instance, to get a PhD in physics and end up doing astronomy anyway, right? And there are a couple of flagship institutions in that. Now, a typical trajectory too kind of goes as well, and that is that you would want to go and take some time. Um, oh boy, why am I going to do this? So you want to kind of like hone your skills. You want to hone your skills after you get that PhD. So you get sort of like additional sort of like experience under the mentorship of someone else. And of course, it's Friday and my brain is fried, and I can even think the word that I'm looking for right here. It's not an internship because I'm thinking, Jeff, help me out. What do we typically do after we get a
Fellowship? Oh, postdoc.
postdoc? You know, postdoc. There we go. That's what I meant to say. Oh, it's a Friday, you guys. It's a Friday. Yeah, you go and get a postdoc. And I chose not to go that way because I had the itch to go and teach, right? And one of the things I didn't get around to talk too much about is that I also do research in astronomy and physics education. And I was itching to try some of this teaching techniques that have been research based in the classroom and being able to bring it to the school. So I knew that I was taking a gamble, and I think that's paid off because instead of going to, say, an R1 institution, I went to what's called the Regional Comprehensive Institution, whose primary focus is undergraduate education, right? So I still get to do research. I still to do things. Maybe I don't have the research that will bring you both the big money as well as the big papers. But I've made a deliberate choice to have research projects that actively involve show the community, undergraduate students, and kind of hone my skills in that so that those undergraduates and community members have a rich learning experience. Here's one thing that I've done too that I didn't get mentioned to do. I engage K through 12. I've had middle school kids have observation campaigns of exoplanet transits. And I'll be darned if those middle school kids did, as a class as a whole, measure and create a graph of the change of brightness, a light curve of a planet covering a star very briefly. And I'll be darned if they didn't actually submit that to a database by the Harvard Smithsonian Center for Astrophysics that actively engages K through 12 students in having that experience. So that was my choice, right? That was my choice as well. So I'm actually very grateful that I'm in a place that allows me to do that.
Super cool. Um, any last questions, Jeff, or any students in the room?
So if I could chime in with a few more kind of questions about the cataclysmic variables that you were discussing. So selfish question time. Do you have any time lapses of of some of these these variable stars, something going into the nova state and then the decay from that. Like
Yeah.
I caught RSO a few years ago, but only kind of a few days after peak, and I just have not been able to find, good resources for showing students what these things look like over time, right?
Well,
Lots of kind of stills, but
do that. So yes, I do. Yes, I do. I have this for our library. Here's the thing, and this is part that's interesting, is that for cataclysmic variables, um, it's not very dramatic. It's not
Mhm.
quite drum blowing, but I do have some of these time lapses. And actually, no, this time lapses would be to a grandiose term to use. Essentially, we're talking about GIFs. Essentially, kind of like dim, bright, dim, bright, dim, bright, just so you get a sense of doing this. So yes, I'll be very glad to kind of like email you back and show you some of these things that I've prepared for my students. So why
Oh, thank you. And not to put you on the spot,
not?
but this is one of those things where, sort of, this proliferation of telescope access um, is really opening up kind of new opportunities. And so I'm really glad to see you discussing the work that you're having students doing, using these observational resources. So,
Yeah, so we have a couple of telescopes that are going to come in line pretty soon that essentially will image the entire sky several times a night indefinitely. So, for instance, we have the Vera Rubin Observatory that would surveys, as well as, for instance, the Argus Observatory is essentially being built, and that's the entire premise for that. So the idea there is to actually catch things that are weird, catch things that are changing, things that are very uh, really quickly throughout the night, and the possibilities for public engagement and citizen science to engage with this are absolutely tremendous. Why? Because there are not enough eyeballs to do that. That using AIs to kind of like search for patterns of changing of brightness is one of the things that is in active development. But really, this is where we're doing. You as a citizen could essentially look at a variable star and decide to adopt it and essentially monitor it and report observations of the changes of brightness to a VSO, and that's going to be valuable. So right now, kind of that's happening with private telescopes as well as robotic telescopes. And these are things that you have to pay access to, but the ability to do for more, really kids, like I'm thinking K to 12, to do the thing that I did with a pair of binoculars over 30 years ago, in right there in the Santa Clara Valley, right? It's like waking up at 2 o'clock in the morning to monitor a variable star to send to a VSO. What was I thinking? What was that all about? But anyway, I thought that was a very private thing, but the possibilities for anybody to have their own star that they kind of like monitor and see how it changes for fun with these tools, it's now possible.
I love, maybe we can end on that note. Just, I think that idea, I think we often think about science in these solitary ways, the person in the lab, the person at the telescope. And I love the quote you read at the beginning, Jeff. If that is indeed what you wrote, Dr. Gomez, just the idea that science is, yeah, such an opening for community building that hopefully we all remember, especially those of the students here that are going to be going into STEM in all the different ways. Dr. Gomez, do you mind leaving in the chat if there is an email address that students could
Sure.
use to reach out to you? And
Absolutely. You're welcome.
meanwhile, just want to thank you so much for your time, especially knowing that you are 3 hours ahead. So it is really the tail end of your day going into the weekend. And can we all just thank Dr. Gomez for your time, for joining us today? Really, really appreciate the engaging talk that you shared with us. So thank you so much. And thank you all for the participants who are here. I'll be sending out a recording if you all want to review this again and of any follow-up materials. So thank you so much on this Friday afternoon, Dr. Gomez. Have a wonderful weekend.
Please take care. Cheers.
Take care, everybody. Bye.